It is a pleasure to introduce Kathryn Mann, PhD 2014 from Chicago, now at Cornell. And the title of her talk is
Anosov Fllows on 3 minutes. Thanks very much. Thanks for the introduction, and it's such a pleasure to be back here in a room where I'm still too short for the boards, so something has not changed. This talk is going to be about flows classifying particular kinds of flows on 3 manifolds. So I want to give you just some examples of a class of flows to think about. A flow is a one-parameter family of diffeomorphisms of some manifold. A nice big class is geodesic flow. So what is this? You take the one-parameter family of diffeomorphisms. T is my time parameter. And on a manifold, which happens to be the unit tangent bundle of some other manifold, maybe I'll use M and reserve M for something else. So N here is some Riemannian manifold. And for each time, I have a diffeomorphism, this unit tangent bundle, and I'll draw you a picture of what it is. Maybe for the sake of illustration, we pretend N is like a round sphere. And I take a tangent vector, unit tangent vector, and I can apply my Riemannian exponential map, get a geodesic. I travel along this distance t, and I'll take the point, the tangent vector for this geodesic, distance t along, and that's phi t. That's the definition of what this is, and for each t, you get a diffeomorphism. This is when I compose them, it's additive in t. That means I have a flow. I can see. Also, I can track individual trajectories of things. Now, when N is the round sphere, like my picture, this is not a very interesting dynamical system. All the orbits are periodic. And in fact, with exactly the same period, if I follow around, I'll come back at exactly, at the same time, every point will arrive back at itself. The trajectories are predictable. Meaning that if I take a nearby tangent vector, okay, the path that it follows is nearby to the, to its neighbor. But the system as a whole is not stable. If I change this a little bit, for instance, if you perturb your metric a bit, maybe you now instead of a round sphere, it's an ellipse. Logically, this would be the same manifold. But you'll quickly break this kind of periodic with the same period. If anyone's ever done the, Riemannian geometry, trying to find all the geodesics on an ellipse, it's a hard problem. So the system, despite sort of on a micro level, individual trajectories being very predictable, the system as a whole is almost chaotic and perturbed and get something qualitatively very. These kind of observations is what we like to do in dynamics, or some version of dynamics. You could also describe geodesic flow by writing down some second-order differential equation. But the sort of global behavior is less obvious from that. Okay, so not so interesting, but if instead N has negative curvature, the point I want to make is that it's qualitatively the opposite of this phenomenon. So here's my bad cartoon of a saddle-shaped thing. On the level of individual trajectories, negative curvature leads to unpredictability. I can take very nearby points in my unit tangent bundle, and they will follow paths that diverge, typically at like an exponential. One way to think of this is it's kind of like iterating a linear map with eigenvalues off the unit system. So maybe I just have this matrix where lambda is greater than 1 or something like this. And I think about it acting as a linear transformation of the plane. If I take 2 points at random, even if they're close together, unlucky, and the difference between them was in the like contracting eigenspace, which here I guess I drew with like a vertical direction. Unless I was extremely unlucky and this 0% chance they happen, as I iterate my 2 points, the distance between them will grow exponentially. So individual trajectories are not predictable at all. But actually, in a precise way I'll define in a minute, the system as a whole is very stable. This observation is due to Anosov, and the reason for it is not actually something to do with the fact that you are on a unit tangent bundle, but more something to do with the fact that you are like iterating a matrix. There are well-defined directions of contraction and expansion at every point. So the abstract definition of this, what we call an Anosov flow, and that's the definition of my type. All right, so here's the definition. A flow phi on some manifold. I need a metric to write this down, but it's going to be independent of metric. It's called Anosov. If it has directions of contraction and expansion at every point. Okay, like my matrix. So what do I want? If there exists an invariant continuous splitting the tangent space to my manifold, as there's the direction the flow goes, there's a contracted direction called the strong stable direction, and well, or directions, it's some plane distribution, and there's an expanded one called strong unstable. Okay, what do I mean by expanded and contracted? To formally write this, I would like to say, edit flow direction here. Okay, so here's the way to make this precise. There exists some constants. This will let me say it's independent of the metric. So that if I take some tangent vector in the stable subspace here, and I apply the flow. So I mean, this is just the differential of the map, what it does to tangent vectors. The norm of this decreases by a factor of c e to the tk. So exponentially with time for all t greater than. That's what I'm saying, an exponential direction of contraction. And if I wanted the expansion, if I want to be clever, I could say the same thing for the unstable one, same, like here I should put an absolute value of t because I'm going to go backwards in time and say it got contracted in the past. So like expanded in the Anosov in the 1960s called these, he didn't call them Anosov flows, called them new systems.
This is a horrible name. And that's what you should do too if you want something negative.
He observed that geodesic flow.
Do you mean in this inequality that k has to be positive?
Oh, sorry. All of these have to be. Both of these should be positive. Thank you. So geodesic flow on the unit tangent model of a negatively curved manifold, and in fact, we even have tiny little pockets of positive curvature. This is an example. If you have played around with this kind of stuff before, this gives you sort of a horocycle foliation for common objects in geometry. But more interesting than this, the theorem is that anything satisfying this abstract definition all Anosov flows are what's called structurally, or say C1 stable. Meaning any C1 small perturbation, you can think of that as just being perturbing the vector field that's generating your flow. Any sufficiently small C1 deformation of an Anosov flow changes it only in the most obvious way. So what could you do to change something a tiny bit? One is that you could reparameterize time, right? You could just like go at 1.1 speed or something like this in some area instead of 1. Okay, so that's something you could do. The other thing you could do is you could just do a global change of coordinates, conjugate the whole thing by the homeomorphism of your manifold. Anosov said this is exactly the only things that can happen. So a small perturbation is C1, yeah, perturb is what I found by small.
Sorry.
I'll put small for my room. It's just time change in conscious. This notion is so important. I'm gonna give it a separate definition. I'll say it in a different way. Otherwise put, it's what we call an orbit equivalence. So, all right, I'll give you another way to say time change and conjugacy to do a definition. If I have two flows, phi and psi, on a fixed manifold, these are orbit equivalent. If I forget time, so I'm left with time change. So then I just see the paths traced out by the orbits of these as I see my trajectories. I don't know how fast you're traveling. And I want those to look the same from the manifold's perspective. So if there exists a homeomorphism of the ideal manifold that just takes orbits to orbits. The topologist definition in history, forget the motion, you just see a foliation by orbits and you want these. So this observation that Anosov flows have stability says that there's some hope that you might classify them up to orbit. This is somehow the right notion to do a classification because it's up to the obvious perturbations. Let me write this down. C1 stability of the Anosov flows means that on any fixed manifold, or I guess on all manifolds, there's only like countably many smooth manifolds, there's only countably many examples total up to orbit equivalence. So in theory, you could list them all, right? There's some hope to classify all of them by some kind of discrete algebraic or numerical invariant. And this is a perspective actually that was advertised by Smale and his 1966 IPM address. In this, actually, a beautiful paper written along to go along with it, he gives a very clear picture of what he thinks a classification will be in like a discretized version. The like actual iterative matrix version, where instead of a continuous system, you just take iterates of a single homeomorphism. There's a counterpart called an Anosov homeomorphism. And he has a good conjectural picture, which is in some sense almost true today, of what all possible examples are in situations of variation. And for diffeomorphisms. along with that, he names the problem of like, we should obviously be working on this flows thing, but doesn't have a hint of what the invariants for classification might be. And I think,
what the examples are?
or what the, so at this time, very few examples were known at all. And I don't know, I wasn't there, you know, some people probably thought that there just weren't very many examples. What was known was geodesic flow and negative curvature. And an example you can build out of a matrix by like taking a suspension. So you build a mapping torus of something like that. Well, about like a hyperbolic linear automorphism of a torus or a nil manifold, and you can continue this kind of suspension flow. Very up. That was it. 1967. That was the only known examples. But it's more interesting than that, especially in dimension 3. So I should say we don't know what the library of examples is even now on high dimensional manifolds, but on 3-dimensional manifolds, such as, you know, surface tangent models, geometric manifolds, there are lots and lots of examples. So in around the 1980s, we discovered lots of new examples of non-algebraic Anosov Fllows on 3-dimensional manifolds. This work is due to Franks and Williams. Handel and Thurston have a joint paper. Sue Goodman develops a technique. David Fried also. These all use some kind of cut in paste or a surgery technique. So imagine, here's a cartoon thing. Imagine you have an example of one of these flows, and you happen to have a surface, for topology reasons, it always ends up being a torus that was transverse to the flow. So you could cut your manifold in half, and everything is just outgoing from one side to the other. If you could find such as this and 2 different examples of manifolds, then you could take half of one and half of the other, and glue outgoing to incoming, and you produce a new manifold that was sort of a hybrid monster of these two with a flow. And then you have to be very careful about your gluing. There's lots of ways to bring 2 things together to make sure the resulting thing is Anosov. So this work of, you know, 5 or 6 or 10 people over the course of a decade produced a library of techniques like this. Also, a way you can drill out a closed orbit into a Dane surgery technique and carry the flow along. But of course, if you do one of these operations, you're changing not just the flow, but you're changing the ambient 3-manifold as well. And so there was a question in the air of like, when you have a fixed 3-manifold with many distinct up to orbit equivalents, flows just on this one space. Okay. All the existing techniques change the space at the same time. This all sort of date 90s to 2010s. There was a different industry of techniques. Using kind of assembling building blocks. And maybe the epitome of this technique is a result sometime in the 2010s. I couldn't write it down. Of Began, Wanati, New, who show for the first time that for any number 100,000, they can build you by hand a 3-manifold compact closed 3-manifold with 100,000 or whatever n was these and distinct up to orbit equivalents Anosov Fllows. So it's thing I'm always going to talk to these about. If I forget to write, they're always up to a part of it. I think this was why, okay, this played out over sometimes people became more convinced about the flexibility of these constructions, but to someone in the 1960s, this would have been extremely. And this is why perhaps that Smale didn't have an idea of what the classification should be. We just had no idea. These building block things are always glued along tori, just that's the way they work. That's kind of what you can put in good position. And so it still remains open that if you do this in like an atoroidal situation, or was the classification going to use like cutting your manifold in along tori and simple pieces and understanding the pieces? And a couple of years ago, even more like 2020, Jonathan Bowden and I showed that actually tori are not the secret to producing lots of examples. We showed that the same thing is true in tori with no, injectively immersed, in manifolds with no injectively immersed tori. So for all n, there exists a toroidal or geometrically hyperbolic discrete manifold with at least n distinct Anosov. So the point of this history lesson is maybe to tell you that there is a whole zoo of examples in dimension 3, and really the classification problem has two parts. One is sort of what has been worked on, here over decades. Understand which three manifolds have examples of Anosov Fllows at all. So since the early days, we knew some constraints. For example, you can use old work of Pont to show that what's a good sample? To show that the manifold must be aspherical, so its universal cover is homeomorphic to RG. So irreducible, for instance. That's something that's been known a long time. And then there's a second part, which received a lot less attention until we knew that there were tons of examples. I'm given some three manifold, which might have 200,000 distinct Anosov Fllows on it. How am I going to tell these apart? What invariants distinguish all the flows, all the Anosov.
You also have a constructible. Isn't that the existence?
Yeah, this is the existence. I would say so that this really you have to play at both ends, right? Abstractions, what will or will not, and then constructions, which oh, I see. How to construct all possible ones on a given manifold.
What is that about?
Sure, I don't know. Throw that in one of these categories. Yeah. Yeah. How many or something, or what are they, or something like this.
Obvious. Very easy obvious that the number is 5 or not.
This is an important open question that we do not know.
Oh, we don't know.
So now we know there can be arbitrarily many, even if you have a somehow geometrically simple manifold or topologically simple manifold. Does there exist a manifold with infinitely many? That's open. I believe it's conjectured generally. I've heard some people with some ideas. We hope that we have, the point of this talk is to tell you a theorem that is going to answer this part of the classification problem by what Smale wanted some discrete algebraic invariants that should give us a lot of help towards this funding. Yeah.
Can I ask a question about how the question is formulated?
Yeah.
When you say that there's an Anosov flow, you can perturb them, there's not Anosov.
Yeah.
In the space of all vector fields, there are these blobs, which are Anosov.
Yeah.
And you're not really asking what are the blobs. You're allowing your first classification. You're allowing jump to different principles for the classification, right?
Yeah.
So is the answer is different if you ask which flows can be formed into one another?
Yes, if I allow global deformation, this is a different question.
Like for geodesic flows, you can have manifolds with different structures.
Yeah, so Amy has an example which about just in the realm of geodesic.
Maybe that's what you're saying, but in principle, the flows would be on manifolds which are homeomorphic but not equal.
Yeah. So, right, this also I'm very careful to say homeo here.
Yeah, that's what I was saying too.
Yeah.
There are examples.
Other questions? Okay. So on this half of this part of classification, the top part has received a lot of attention. We don't totally understand it, but we have many constructions, and that's just a sample of some obstructions. These have not met perfectly yet. I'm going to talk about the second part, which is given some examples, some manifolds, how am I going to tell all of these? Okay, so here's maybe the coarsest thing that you could, piece of topological data that you could write down. Okay, while we're doing this sort of palette cleansing pause, let me remind you that this is like an interesting problem, not just because Smale said so, but because these are beautiful examples of dynamical systems. Where's my cartoon? This divergence of trajectories is like it's the simplest example of chaotic behavior, right? You take a slightly different initial condition and you try and follow it and you get something unpredictable. You want to understand like chaos in nature. This is a nice toy, well, not toy, a nice model for this occurring, in a way that we can try and we're really optimistic, understand and classify completely, at least in the moment. All right, that's a why we should all. Okay, so let's classify them. Here's one invariant I'm used to tell things apart. So I have a flow on a manifold. Some of the trajectories will be periodic, and some will not. They'll never close up. Well, unless I was on the grounds here in my silly example. I could just write down all the periodic trajectories. So what is that? That is a collection of loops in my manifold. So this will be the set of periodic orbits. So I don't need an Anosov to write this down, but that's the context I'm going to be talking about. So for phi t of flow on some manifold M, the set of periodic orbits of periodic data is the set of free homotopy classes represented by periodic orbits. So here, gamma equivalence class I'm thinking of is a free homotopy class, so that's the phi 1 up to conjugacy. And I want either gamma or my definition of orbit equivalence doesn't say I have to preserve the direction of the flow, so I'm not allowed to pay attention to direction. Gamma or gamma inverse is represented by a periodic orbit. Have a foliation, you write down all the loops. Okay. Observation. If I have some orbit equivalence flows, then this data agrees. Right? So a nice way to put this, let's say if F is an orbit equivalent to between two flows, I and phi, then the periodic orbits of phi are those, well, what happens when I apply f to the ones from phi? So whatever my boost map is on boost, I send one to the other. If f was isotopic to the identity, then these sets we just removed. And in work with first with Thomas Barthelmé and then also joined with Stephen Frankel, we showed that basically this is actually all the information you need to complete invariant. So I'll state a simplified version first, in which it really is a complete invariant. This is two separate papers because there were actually two different sets of techniques in different situations. My simplifying assumption is going to be that the manifold is hyperbolic, right? And then I will remove that in a second. For M hyperbolic, I'm only doing toroidal. This is a if and only if the converse is true. So, I want two Anosov Fllows. Their sets of periodic orbits agree if and only if these are orbit equivalent. Oops, and the way I've said it, that they literally agree is via some map isotopic to the identity. And equivalence is because actually the types of manifolds that support Anosov Fllows are all K-1 spaces. So I can edit this just like I did before, and say that if I have some map on three homotopy classes induced by some automorphism of, the fundamental group of your manifold, if these agree up to applying some automorphism, then your flows are the same by some orbit equivalence, inducing this map. So I want to give you maybe some hints of how this is proved, why this invariant is somehow enough to capture everything. Before I do this, I'm going to state for you the general version where I don't make this assumption. So let me start to edit this out. Okay, and this is the point where you don't take notes unless you're a three-manifold topologist. And if you are a three-manifold topologist, you take careful notes and you appreciate how delicately the theory of Anosov Fllows is linked to three-dimensional geometry of topology. So while what I'm going to state is technical, the point of this technicality is to show you that it is actually very nuanced and plays well with the torus decomposition of three manifolds. Here's a crash course in three-manifold topology, right? You have a three-manifold. Either you can prime some, decompose it into irreducible pieces, right? You can do that first. You have an Anosov flow. We knew for a long time that actually can't happen. You end up being aspherical. That's not crazily hard. So okay, now I have an irreducible three-manifold, and there's a further decomposition you can do, cutting it not along spheres but along tori, called the JSJ decomposition. The resulting pieces are either ciphered fibered or atoroidal. in certain cases, the Cypher fiber pieces contain some extra information you have to keep track of. So for arbitrary three manifolds, there's a complete invariant that has a little bit more data than the set of periodic orbits. Okay. So if I want to know exactly when two things are orbit equivalent, I record all the periodic orbits, and here we go. For each Cypher fiber, piece of the JSJ composition of your manifold, where the fiber and not just the fiber, also independent directions or homotopy classes, elements, and each boundary torus happen to be represented by periodic orbits. Of the flow, so you see them in this list. Okay, should this happen, see it in the list for both sides, I need to record one extra thing, which is a plus minus sign. So here's my invariant with the three homotopy data plus with these very special topological regions. I want to say the signs. So the upshot on one level is that basically periodic orbits are a complete invariant. The upshot on level 2 is sometimes you need extra something a little small. Yeah, Amy.
Do you assume any irreducibility of these flows?
So in my first version, no, it comes for free. Here I need one to be transitive. Yeah, thank you. Assume I can, at least one is transitive. But it's transitive. Yeah, so I need a dense orbit, and what this does is it gets me lots of periodic. So actually, if I go back here to what did Smale actually ask, you can go and read his words. He suggests one classifies transitive Anosov flows, these being kind of like the basic building blocks from which you produce, well, the sort of the base case to understand. Non-transitive ones you can decompose in a natural way into invariant sets. You would try and then understand these sort of pieces that way. Okay, so that's the classification theorem. Maybe in 1 second I'll say this was pretty recent and an ongoing work. A recent paper with Sergio Fenley. We make this whole three manifold topology picture very precise. We actually build examples, so show how to kind of do a cut and paste to preserve periodic orbits and do one of these weird sign flips on a Cypher fiber piece to show that this is like the best possible invariant we can possibly write down. I don't want to talk about that because it gets quite technical and quite into three manifold topology. Instead, I want to spend our remaining time giving you a picture of a tool for the proof of this, and you can assume it's the easy to state version. And that tool is to take this kind of continuous time system on a three manifold and change it to a discrete dynamical system on a lower dimension. The setup, and the setup actually is due to a perspective of Kathryn Mann and Sergio Fenley working in the 90s, first independently and then together. How you can study these objects. Here's something I'm going to do. I'm given an Anosov flow. I can lift this to some flow on the universal cover. And I told you that this happens to be, I can prove it's a theorem, that this is homeomorphic to R3. So now I have a flow just on free space. And I can if I want to understand things of the orbit equivalence, I should just be looking at orbits. Now the orbits are not tangled up or anything. They're just in free space. They're all on and stuff. Collapse each orbit to a point. Collapse orbits to points. So the definition is the orbit space of my flow. This defines the universal cover quotient by, x is equivalent to any point in its orbit. And Bowden and Fenley show theorem that this is homeomorphic to a plane. Topologically, it's a plane. So it's not hard to show that it's some two manifold. It shows that it's Hausdorff, you have to do a little work. And it's simply connected comes from it comes from the issue of sort of making a nice quotient of part.
That free universal cover?
Oh, sorry, yes, thanks. Okay, so that's the orbit space. My definition of an Anosov flow here gives me extra topological data. I don't just have a foliation by orbits, but it's a theorem that so here, if I'm in dimension 3, all of these are one-dimensional. I only have 3 dimensions to work with. This is tangent to a foliation. This is actually an integrable distribution. I think I waved my hand saying something about, first year foliation, first cycle foliation in geodesic flow. And if I do this, there's nothing special about S where time was positive instead of negative. This is also tangent to a foliation. All the unstable. So I can live these foliations, and my universal cover now has some two transverse two-dimensional foliations. These descend to this orbit space. The point of all of this is that this is not just some kind of arbitrary copy of R2, the plane. It has two transverse, now one-dimensional foliations. They're really coming from these directions. So I'm going to hide this again, right? With transverse, one-dimensional foliations, which by abuse of notation we call F stable Fs.
Is there a picture?
Yes. Yeah. So let me draw a couple of cartoons of this. For geodesic flow, I can tell you exactly what this space looks like. If you take M3, is the unit tangent bundle of some, I don't know, say like a genus 2 surface or any negatively curved surface will work. Okay. Then and phi is geodesic flow. Then the orbit space that you get, you haven't thought about this before, but you know a little hyperlog geometry and geodesic flows. Beautiful exercise. It looks like, I'm gonna draw a picture where my plane is gonna live inside this sort of like infinite diagonal strip. That's a weird way to draw R2. It's totally back to R2, so let's do it. The foliation is gonna be vertical for one and horizontal for the other. Okay, this is fire. Exercise, why does it look like this? That's a really fun thing to think about. And why did I draw it this way? It's not the usual trivial foliation where like in a product foliation, every leaf crosses every leaf. Here I have some orange leaf and some blue leaf that do not meet at all. Because it's the premium of the blue leaves that meets the given orange one. How they're stacked. This is actually not that typical. Typically, we have some very interesting geography of this space. The space of leaves of either one of these foliations is typically come across Hausdorff. You see something like a collection of leaves that accumulates onto some union of the same foliation. I can have this happen to both. So I see some that are like can't be separated from each other by open sets. And I'll see this happening kind of everywhere on different scales. It can be very complicated. Great. So I have something topological. I don't have any dynamics yet, but I do here. The fundamental group of my manifold acts on its universal cover by deck transformations. Everything here was lifted from the manifold downstairs. So I get an action on this quotient space by the homeomorphisms of the plane that preserves the foliation. These are invariant under this induced action from the set. Okay, and the beautiful thing is that this is complete information if you want to understand flows up the orbit fluids. You know, I think fluids are the Barthelmé, but in this, the way I'm going to state it, you can give a quite a simple proof, which is that if I have two flows, Anosov flows, I give a manifold. These are orbit equivalent if and only if actually, let me do the cheating way where I say by something isotopic to the identity, and you can go and insert in up to an automorphism to make it true in general. By F isotopic to the identity on half. If and only if the orbit spaces are the same and the actions are conjugate. So there exists the Julio 8 of these orbit spaces as foliated planes. So it takes the pair of foliations to the pair of foliations. And conjugates the action. So to classify flows up to orbit equivalence, we just need to sort of understand the actions of three manifold groups on bifoliated planes up to conjugates. Here's an easy fact. Periodic orbits are things that represent three homotopy classes of periodic orbits. Gamma here is an element of my fundamental group because it's conjugacy class. I can see that it was a periodic orbit by looking at the dynamics of the fundamental group acting on the orbit space. This happens if and only if the action of gamma on the orbit space of my flow has a fixed at least one. Okay, let's do one direction to see this. Let's do that direction. Suppose you act on this orbit space with a fixed point. Fix this point. This point represents an orbit. Okay, so what does that say? Before I took this quotient, when I was back up on the universal cover, the R3, the deck transformation that gamma is doing moves along this orbit and preserves it. Right? So that says that it takes some point on the orbit and moves it back up to itself. Downstairs on my free manifold, it would got moved into a circle on the periodic orbit. The other direction is the same kind of thing, just say that all back. Yeah, well, you know, just reverse all of the arrows in your criticism and it back into your CNA. Okay. Okay, so this says, so what is the translation of this theorem? What we actually do, we developed a theory of Anosov-like type actions of groups on bifoliated planes and show that you can recover them up to conjugacy just by knowing basically what elements have. Right here to redevelop a theory of what we call Anosov-like actions, not just of three manifold groups, but just of general discrete groups. On bifoliated planes. Anosov-like is a set of 4 or 5, depending on how concise you are, dynamical axioms. So for instance, the first axiom is a local expansion contraction. Some element in your group fixed at some point. What's my plane? My plane used to be an orbit space, now it's an abstract plane. Then P is on a plane with 2 transverse foliations. I will see these. So 2 leaves, 1 of each for P. If I iterate G, it fixes this point. So the leaves through it are preserved. And I want one of them to be contracted because I iterate points go towards P. And I want the other one to be extended topologically. So as I iterate points go over. That's axiom number 1. The other one says something. This slightly not much more complicated. It says that you have a behavior that on an element lines level looks like the kind of stuff you get from an Anosov flow in its flow. Some sense strictly more general. Okay, so we study this and show that such actions can really be classified up to conjugacy just by knowing just a list of elements of your group that happen to act with fixed points. This is exactly what you need to do. Maybe I should say, I said this vaguely enough, but I don't think I actually lied. This is exactly what you need to do to translate back up to the orbit space and say, if I know periodic orbits, I know my flows up to orbit. I'm happy to give you some cartoon pictures of why you might hope to believe that. It seems a little bit crazy. I get a list of algebraic data. I'm supposed to recover an entire, not just the action, but actually the structure of the plane, right? Like, did it look like this or did it look like this? Right? And I can read this off of a list of elements of a to do that takes many pages building up machinery, saying what can I do from algebraic data. I'm going to give you some tricks later to convince you why you might believe there's a hope that might be true. But I think I've come to at the end of the hour now, so I will stop and say thanks very much for your attention.
Question? Anything known about Anosov Fllows on the tire?
So there is a very recently proved conjecture by Barthelmé that says that with one constraining assumption, the one you might try and make to repeat this stuff, there are very few examples. So except in dimension 3, if you have what's called a codimension 1 Anosov flow, which says that at least one of your like say the stable foliation was codimension 1 on your 17-dimensional manifold or something, then these are only algebraic examples. They all come from suspensions of like essentially linear, well, of Anosov diffeomorphism on toric and manifolds, things like this. So that's exciting. That's strong rigidity. There is one, not quite cut and paste, but surgery type technique that you could do, sort of a codimension 2 phenomenon. And that's it.
But
so,
nothing's known about like whether or not we have this case.
What do we know? Even all of this kind of stuff is done like codimension 1 mostly. I'll have to think about aspherical. Yeah, I think this is mostly known in this codimension 1 setting. Yeah, it's very mysterious. I'm not much.
Where does the signs from the cipher fiber stuff show up?
So this is the imprecise thing where
right.
I said here, I was like just, and I was like, I don't know, essentially. Okay, so what do you do if you have the same list of elements with fixed points? Let me do a cartoon picture. Suppose you do that everyone's fixed point has exactly one fixed point. Okay, I'm going to try and build a map from plane to plane by sending the fixed point of G for its action over here to the fixed point of G for its action over here. Great. Oops, some elements have infinitely many fixed points and things like that, so that's hard. But you can, if you're not in this looking setting, you can find enough to have a single fixed point, but this is defined on a dense set. If you have this map, and if it was continuous, then you would extend it to a homeomorphism between your planes of conjugated the action, because it's natural. And it's typically continuous, and it can only fail in exactly one way, and that's what this sign thing does. And just understand this map completely. Yeah.
So for a given 3 manifold, can you use this to figure out exactly how many orbit equivalences? Or
this is what we want to do, or at least say there's only finitely many. Okay, so this is some input into that program. You have your complete invariant. We don't know in practice, so I think some interesting questions are like along the lines of like, what does this set look like? It's some subset of your three homotopy classes. You can ask various like asymptotic count type questions of like, is it a lot? Is it most? Is it like, you know, as you take larger and larger samples, you get, you know, 100% asymptotically of things, or is it small? You can ask, you can, you know, we can show very easily that it's not everything. It's, but I have nothing solid to say on that. What it's being used for right now is it, you know, some of this is being fed into some machinery. I'm not an expert in contact homology, because there's a theory of contact Anosov Fllows that gels very well with this, and that kind of stuff gives you even more powerful invariants, which is what people are using now to attack finding this. But you know, there might be a bypass version of this too. I don't know.
Any questions? Before we thank the speaker again, is there going to be a dinner, or is that you want to tell people if they're interested?
So I already made a reservation. It has to be full to the first family, so I'm not sure if it's.
Okay, so if you're interested and you didn't sign up, that's too bad. Although you could.
Come chat with me now.
Yeah, I encourage everybody. Are you going to be around?
I'm leaving tonight.
Okay.
That's okay. I have an email address that you can find. So, you know, the world is small. Oh, my question.
Yeah, I was just wondering, did you draw the picture that you're talking about to get some justification, or was that the
let me give you a very, like a 1 second free map picture. All right. So, suppose I have someone with exactly one fixed point. I believe that you can find things like this. It's a cartoon picture, right? So this is G, what it's doing. And in my group. And I have some other element in my group, it acts on the plane. Maybe it takes the fixed point of G over here. And so now I'll see a picture where the conjugate of G by F has this kind of dynamics. Back in there. So this is, what should I write for that? If this configuration happens, if I take, just by looking at how these things, you end up doing some Brouwer fixed point theorem type of things, like what gets contracted. If I take any giant iterate of G and follow this by any giant iterate of FGF inverse, and N1 and 2, will always act on the plane with a fixed point. Okay, so this gets recorded in my list. Versus, if F took this somewhere way far away, maybe over here, so these don't cross each other anymore. Okay. You can play a game and you can find something like a dyne power 1 followed by a dyne power the other that does not have a fixed point. You have to do some work to find this. And so, knowing the list of elements with fixed points tells you something about did F move something very close by or very far away. Okay, that's the kind of game that you have to play. This is really just a local picture. Right? So what I was trying to draw with the wrong colors is something that happens, here and here in number 1 versus something that I guess I could have drawn something like that over there, but that's a little more complicated versus something like, up here. Maybe over in this tiny little topic where they don't interact at all. And that's the heuristic that you might be able to tell something about the topology of the dynamic.
Okay, let's